Hey there, in this video we're going to cover what is possibly the most popular algorithm in computer science. Binary search is the subject of most technical interview coding questions. So stay tuned, we're going to see it right here on Eliminate Code Fear. Binary search is one of the most popular algorithms in computer science, and rightfully so. It's actually one of the fastest approaches that we have for searching through a list of things, right? There's a famous book, it's a classic, I recommend you read it. It's called Programming Pearls, and in there, the author John Bentley mentions that only 10% of professional programmers are able to implement binary search in an interview, right? Only 10%. And that's also been my finding. Every time I ask binary search in an interview, the candidate kind of is not able to code this up behind the keyboard. They can explain it really well because it is a simple concept to understand on a whiteboard, but actually getting behind the keyboard and coding it up could be a little challenging. So we're going to get plenty of practice in the screencasts when we get there. But first, let's go over how this algorithm works. I'll give you an example. Let's say we have a bookshelf of randomly placed books, right? There's absolutely no order to the way the books are placed on the shelf. Let's say that I need to look for a book by the author Shakespeare. I'd have to look at every single book on the shelf to see if it's by Shakespeare or not, right? That's the linear search approach, right? We've already seen linear search. There's no order. I got to look at every single element to see which matches my condition. If the books were sorted, I could be much smarter in the way I approach the problem. I can use binary search. So to implement binary search, the number one condition is the data must be sorted. I'm going to write that up here. If it's not sorted, we got to use linear search. So in the book example, let's say the books were sorted by the author's last name. If I was to use the binary approach to solving that problem, I'll go to the book right in the center of the shelf and see who the author is there. Let's say the author's last name there starts with the letter U. Remember, we're looking for Shakespeare. So we can be 100% certain that any book past U is not going to be Shakespeare. So we can eliminate half of the bookshelf, right? We've drastically reduced the problem size, right? If Shakespeare's on the shelf, it's got to be somewhere in the first half. So then we can do the same thing. We can check the midpoint of this section. And let's say the book there, the author's last name starts with the letter E. Then we can be 100% certain that Shakespeare cannot be before E either. So we can eliminate that part, right? So we're narrowing in on the problem by breaking the problem size in half every iteration. That's how binary search works. So let's implement binary search on an array. Let me get rid of some of this scribble here. So let's say we want to search for the number 78 in this array, right? That's the mystery number. We want to know which index position, which slot contains the number 78, right? And remember, in an array, everything starts from index position 0, goes up to the length of the array, which is 10 minus 1, which is the last slot index, right? Number 9. So the way I could do this using binary search is I can divide 9 by 2. That's going to give me 4.5 in math, but since this is integer division, the half is dropped and we're left with 4, right? So 4 is going to be the midpoint of this array, the index position 4 right here, right? So this slot contains the number 41. Of course, 41 is not 78. So not only is that not our number, it gives us a hint as to which direction we should be looking at. So we can eliminate the first half of this array, right? This is sorted. This is a sorted array. If it wasn't sorted, we of course couldn't use binary search. So keep that in mind, must be sorted. So this data is sorted. We eliminate half of the array. 78 must be in this area, all right? So I can use the same midpoint strategy, find the middle index position here, which happens to be 7, and lo and behold, the number 78 is in that position, right? So that's really how binary search works. It falls in the category of the divide and conquer paradigm. You divide the problem in half and deal with only a subset, and you keep breaking the problem into smaller instances of the same problem until you arrive at the result. All right, so I just cleared the board here to make room for new concepts. I want to go into the implementation details of binary search. How would you code this up in the language of your choice? And to describe those steps, the individual steps, I'm going to list them in a language called pseudocode, which is nothing but English sentences with more detail, step by step, how this algorithm operates to complete the task, okay? And then you can use any language of your choice to implement these steps listed in English, all right? Pseudocode is just a way to easily communicate the steps of a computer program. And we're, of course, going to be we're going to translate the pseudocode in Java, and you're going to get plenty of practice doing this. So here's some pseudocode lingo. It's called procedure. Since this is a Java course, you can just think of this as the method, binary search. I just gave it a name, capital letters. Doesn't really matter what the name is, but what's important here is that this method accepts two arguments, x and a. All right, x is the value that we're searching for, and a is the array in which we want to search that value in. Okay, so we're searching for x in the given array a. All right, and the way I want you to think of this array is like this. Okay, at any given point in time, we're only interested in a subset of the array. Okay, as we break the problem in half and narrow in on what we are searching for, the values of the first slot as well as the second slot, the index positions of those slots is going to be changing, right? So that's what r, the variable r here represents. That's the last slot of the range that we're interested in. And p is going to be the first slot of the range that we're interested in. And q, of course, is the index position of the middle element, right? So these p, q, r are index positions of the range that we're interested in, okay? And when you need to access elements in an array, you basically access them like this, and you can give the index position, whatever it is, 0, 1, 2, or a particular variable I. In our case, we can denote the range by p r, and this will represent the range that we are interested in, the slots of the subset of the array. All right, so let's start listing out the steps here of this algorithm. And keep in mind that this algorithm is supposed to return the index position of where we find x in the given array. All right, if it doesn't find it, it's going to return a -1. So let's get started. The first step is to give initial values to the range, which is the variable p and r. So we can say p originally will have the index value of 0, and r will have the index value of the length of the array minus 1. Whatever the length of the array is, we can say a dot length minus 1. Okay, that's going to give us the last slot. So we give it initial values, and now the range is only going to get smaller. And how is it going to get smaller? We'll have a loop in which we're going to be checking for certain conditions. So step number 2 is we can have a while loop. While p is less than or equal to r, we want to do something. And I'll list those steps here. But what I want you to keep your mind focus on is this condition where p is less than or equal to r. What does this mean? Well, when we're searching through a range, of course, p is going to be the first slot and r is going to be the last slot, right? So as it narrows down, there's going to be a point where if we can't find a given value in the array, r is going to try to cross over p as we're narrowing in. And there's going to be a point where it's about to cross over and we will have to exit this loop, okay? So as long as p is less than or equal to r, we're still going to be in this loop and we're still going to be breaking the problem down in half every iteration and trying to find the x within the range, okay? And once it breaks out of this loop and it continues on, we weren't able to find the value that we're searching for, so this method will return a -1. So let me detail those steps here for you. So in this sub-step, we'll say A, inside of this loop, the first things first, we need to find the midpoint of the range. So the way we can do this is we can say set q to be p plus r, divide that by 2, right? The index position of the first slot plus the index position of the last slot is going to give us the number of slots in the given range. Divide that by 2 is going to give us the midpoint. But what's important here is that we need to wrap this with this notation L. And all this means is flooring the value. Whatever value, sometimes if you get a fraction in the division, you want to floor it to the whole number. And we saw this a couple of minutes ago when 9 divided by 2 was giving us a 4.5. Well, we dropped the half. In integer division, only the 4 is returned. So that's exactly what this flooring operator is. We only want or care about the whole number. And that's going to give us the index position of the middle slot. Okay, we denote that with the variable q. So once we get that, the next step is to check whether this midpoint that we got is this containing the value that we're searching for. All right, and if it is, great, we can return out of this loop and exit the method. So we can say if a at the index position q is equal to what we are searching for, x, then we can just return the index position of q. And we're done, okay? That will just exit out of this method and we've solved the problem. And then the next step is C. We have to consider the fact that q did not contain the value that we're searching for. And in that case, it's going to move on to step C, which is if AQ is greater than x, right? If the value that's in this index position is greater than the value that we're searching for, we know x gotta be in this direction, okay? And in that case, what we can do is we can bring this range, the second part of the range, we can bring that to this slot right here because we know it can't be there. It can't be in that side, right? So we've reduced the range by half, all right? So we can say set R to Q minus 1, all right? And that's going to bring the slot position here for R, right? Else, in the case that the value here is not greater than x, then the opposite is true. Then we know that the data that we're looking for must be in that direction. And in that case, we leave R where it is. We change the value of P, okay? And we bring P over in front of R. We make P point to this slot position. So we can say else set P to Q plus R, plus 1, sorry. Okay? And it's going to continue to narrow in like this as this loop is running. The values are going to be changing, getting closer to what we are searching for, and eventually this step B will find x if it is in this array. Otherwise, step 3 right here is going to happen. What that is it's just going to return -1. We were not able to find the value that we are searching for in this array. All right, so hopefully this makes sense. Let's head over to the screencast and implement this in Java.